do one exercise, and we'll do one of those pumping problems because those are interesting. Suppose in this situation we have a vat that looks something like this. So it has a rectangular top, it has a triangular cross section, and looks something like that. And then it is filled with water to a certain level. Well, let me give you some dimensions here. So there's that. So this is 4 meters here. Let's say this is 6 meters in this direction, and it's 3 meters tall. And let's suppose there is water up to 2 meters. Here's what you want to do. You want to find the work to pump all the water to the top. And in this, you're allowed to use the following: 9810 newtons per meter cubed as the weight density of water. Give that a try. Let's see how to do this problem. We have our vat, and remember it was, in this dimension it was 4, in this dimension it was 6, these are meters, but we'll put those in later, and in this dimension it was 3. And what we want to do is lift out the water. Now what we'll do is the same thing we did in the conical tank, and we'll lift out slabs. In this case it won't be a disc, it'll be an actual rectangular slab, so maybe we can sketch one of those in here. Something like this. And then imagine that this is the slab that we want to lift out of the water. And I'll draw it over here so we can see it more clearly. And in order to lift that out and move it to the top and find out the amount of work, we've got to work our way up to it. That's why this is one of those do-it-yourself sorts of integrals. This is delta y as the height, because I'm going to just go ahead and use y as my vertical direction rather than use x as we did in the previous one. This dimension is 6 because the vat is always 6 units in this direction. And this side will depend on how high you are. So we'll have to figure that out in some way. So let us come down here and draw the end of the vat this way and get a cross-sectional view of it. And put our axes in the most convenient place by putting the origin down here at the bottom. That's convenient. And then this, of course, up here will be 3 because it's 3 units high. 3 meters in this case. And then let's see, across the top it's 4, so that means one side is 2, which means I can write the coordinates of this. This is 2 in the x direction with a height of 3. Well, that's good. And I know that at 2, this is where the water is. And so if I'm looking at a slab that I want to lift out, this slab here, I know that it's going to be in an arbitrary height y, which, by the way, makes the distance to the top 3 minus y, and we'll use that in a minute, because this slab will have to be lifted up to that height to get it out. All right. Then what is going to be the coordinates of a point here? Well, they're going to be xy coordinates, and the x and the y will be determined by this line. What is the equation of that line? Well, the line is of the form y equals, well, it should be mx plus b, and the b is the y-intercept, but the y-intercept here is 0, so there's no b, and I just need the slope. Well, this point lies on the line, and I can think of this as a run of 2 and a rise of 3. So rise over run gives me y equals 3/2 x. Therefore, x is equal to 2/3 y, and x is going to be this distance here on one side, and that's exactly half the length of the side of the slab. So that means the side turns out to be 2x, which is 4/3 y. Now, with all of that work, we're set to write down the volume of the slab and work our way up to the force on the slab, then the work on the slab. All right, the kth bit of volume will be what? Well, you multiply these 3 numbers together. It's 6 times, the side here is 4/3 y, times delta y. Then the kth force, which in this case is again force, is weight. So it's the volume, which is this. Let's see. We can simplify this into 8y, delta y, times 9810, which was the weight density of water that was given to us. And then finally, the kth bit of work, so we went from volume to force to work again, is going to be this expression, the force, which is 8 times 9810 y delta y, times the distance that the slab has to travel here, which is 3 minus y. Oh, and notice that I did not multiply 8 times 9810. It's usually wise to put off such multiplications till the end of the problem. It's easier just to deal with the numbers this way. So, with that set up, we can write work is the integral from, let's see, where the water starts, which is at the height of 0, to where the water ends, which is a height of 2 meters. And then the expression from the previous page, which is 8 times 9810 times y, and I'll put the 3 minus y here, all times dy. This constant, of course, comes out front. The inside you multiply out is just powers of y. So this becomes, after a little bit of work, something that approximates to 261,600 joules. And that's how much work is required to lift the water out of that vat all the way to the top.